Using the inverse to solve systems. A system of n linear equations in n variables x1, x2, etc. xn can be written in the form a11x1 plus a12x2 plus etc. a1n xn equal to b1. Like this, the last equation, mth equation is am1x1 plus am2x2 plus etc. amn xn equal to bm. So we have m equations in n variables. The variables are x1, x2, etc. xn. Now this system of equation can actually be written in the matrix form, and it can be written in the form ax equal to b, where a is the coefficient matrix. So a will take the value a11, a12, etc. a1n. Second row a21, a22, etc. a2n. Like that, the nth row will be am1, am2, etc. amn, which is written here. Now, what is x? X contains a number of variables. So, it has the entries x1, x2, etc. xn. It has also, now we have the vector b. B is the elements in the RHS. So, it is b1, b2, etc. bm. Now, suppose that here we see that A is an m by n matrix. Now suppose that m is equal to n. That is, A is a square matrix. So if A is a square matrix means number of rows and number of columns are same. Again, we can write it in the form ax equal to b. Now further, suppose that A is non-singular. A is non-singular. That is, determinant of A is not equal to 0, which implies A inverse exists. So if A is non-singular, we can multiply this equation on both sides with A inverse. So we will get A inverse AX equal to A inverse B. Now, matrix multiplication is associative, so it can be written as A inverse A into X equal to A inverse B. Now this implies identity I, X is equal to A inverse B. Now we know that I into X will give you X itself. So X is equal to A inverse B. It means that we can solve this system of equation. X is the unknowns. X is the number of unknowns. So we have X equal to x1, x2, etc. xn. We have n unknowns. So we can get X like this. So if in particular, if A is a square matrix and if A is non-singular, that is its inverse exists, then we can multiply both sides with A inverse of the matrix form Ax equal to B, and we get X equal to A inverse B. So in this way, we can solve this system of equations directly. So we know how to find A inverse. We multiply it with the B vector. So you will get the unknown X. For example, we will see this problem. Use the inverse of the coefficient matrix to solve the system 2x1 minus 9x2 equal to 15, 3x1 plus 6x2 equal to 16. So now we see that here we have two equations and we have two unknowns. So the unknowns is written as the vector x, which is x1, x2. Now this system, we can write it in the form Ax equal to B. Now A will be the coefficient matrix. So A will take the value 2, minus 9, 3, 6. So here we have written here, this is the matrix A. Values are 2, minus 9, 3, 6. And X is this vector x1, x2. And B is the RHS. So it takes the value 15 and 16. So we have written Ax equal to B in this form. Now we have to solve this system of equation. So first we will check whether the matrix A is non-singular or not. For that we have to find determinant of A. So determinant of A. What will be determinant of A? It is determinant 2, minus 9, 3, 6. And very easily we can find it to be 39, which is non-zero. It implies that the coefficient matrix is non-singular. If the matrix is non-singular, we can use the formula x equal to A inverse B. So first we have to find A inverse. So in the last lecture, we have explained how to find A inverse in the case of a 2 by 2 matrix as well as in the case of a 3 by 3 matrix. So we know that the formula for, as we studied in the last lecture, A inverse is 1 by determinant of A into adjoint of A. So using that formula, we will get A inverse is equal to 1 by 39. Determinant is 39, so 1 by 39. And adjoint of A, in this case, adjoint of A is 6, 9, minus 3, 2. So now we can write the solution x equal to A inverse of B. So this implies x is x1, x2. Then we have substituted the value of A inverse B. And if we do matrix multiplication, we will get it as 1 by 39 into 234 minus 13. And if further simplification, it will give you 6 minus 1 by 3. So this is our x1 and this is x2. So we got the value x1 equal to 6 and x2 equal to minus 1 by 3. So we have solved this system of equation using inverse of a matrix. So we did for a 2 by 2 matrix. Now we will see for a 3 by 3 matrix. So the next problem is use the inverse of the coefficient matrix to solve the problem 2x1 plus x3 equal to 2 minus 2x1 plus 3x2 plus 4x3 equal to 4 minus 5x1 plus 5x2 plus 6x3 equal to minus 1. So here we see that we have three equations. We have three equations are there and three unknowns are there. What are the unknowns? Unknowns are x equal to x1, x2, x3. So our aim is to find x1, x2, x3. We also note that in the first equation, x2 is not there. x2 is absent here. Only x1 and x3 are there. So first we will write it in the matrix form. So in the matrix form means we will write it in the form Ax equal to B. So A is the coefficient matrix. So what will be A here? So the matrix A will take the value 2 and we can see x2 is absent here. So we can write 0, then 1. Then coefficient of x1 minus 2, 3, 4. Minus 5, 5, 6. So this is our A and x is x1, x2, x3 equal to B. B is the RHS. So RHS takes the value 2, 4, minus 1. So we have written the system of equation in the matrix form. This is the matrix form of the system of equation. So from the matrix form, we will get the matrix A. Now to solve the system, we have to check whether A is non-singular or not. So we see that this is the matrix A. A takes the value 2, 0, 1, minus 2, 3, 4, minus 5, 5, 6. And we find that it's a 3 by 3 matrix. You can find its determinant. Determinant is not equal to 0. And we have explained this method for finding the inverse in the last class. So you can refer that class. So by using the same method, that is A inverse is equal to, our formula is same, A inverse is equal to 1 by determinant of A into adjoint of A. So using the same formula, we will get A inverse. So A inverse we are getting to be minus 2, 5, minus 3, minus 8, 17, minus 10, 5, minus 10, 6. So we got A inverse. Now to solve the system, we have to solve x equal to A inverse B. So we got A inverse. So x is x1, x2, x3 equal to A inverse. We have substituted the matrix A inverse. A inverse B. So A inverse takes the value minus 2, 5, minus 3, minus 8, 17, minus 10, 5, minus 10, 6 into B. So it is 2, 4, minus 1. And if you do matrix multiplication, it is very easy to get the answer. That's 19, 62, minus 36. So we get x1 is our first value. So x1 is 19, x2 is 62 and x3 is minus 36. So if the determinant of the coefficient matrix is not equal to 0, we can solve the system of equation using the inverse of that matrix. Now next we will prove uniqueness. That is, when determinant of A is not equal to 0, the solution of the system Ax equal to B is unique. That is, determinant of A not equal to 0. It means that A is non-singular. Which implies that A inverse exists. The matrix will have an inverse if its determinant is not equal to 0. We have to show that the system, the solution of the system is unique. That is, there is exactly one value of x for which Ax equal to B holds. So we have to show that the solution is unique. So to prove it, suppose there are two solutions. Suppose x1 and x2 are solutions. Solutions of what? Solutions of the system Ax equal to B. So since x1 is a solution, we will get Ax1 is equal to B. Since x2 is a solution, we will get Ax2 is equal to B. Since x1 and x2 both are solution. From this equation, we will get Ax1 is equal to Ax2. Now A has an inverse because a determinant of A is not equal to 0, so A inverse exists. So we multiply both sides with its inverse. So we have A inverse Ax1 is equal to A inverse Ax2. Now, A inverse A is the identity matrix. Ix1 is equal to Ix2, which implies x1 is equal to x2. That is, the solution is unique. We do not have two values x1 and x2. Okay, so the solution of the system is unique. Means that solution is unique. So now we will see another theorem which says a condition for the trivial solution of a homogeneous system. So, a homogeneous system of n linear equations in n variables Ax equal to 0 has only the trivial solution if and only if A is non-singular. Now, what is a homogeneous system? If I write Ax equal to B, which is the matrix form of the system of equation, this is a non-homogeneous form. Non-homogeneous. This is a non-homogeneous system. Now suppose that B is equal to 0. So if B is equal to 0, this implies Ax equal to 0. This is called the homogeneous system. This is called the homogeneous system. So in a homogeneous system is a system of equations whose matrix form is of the form Ax equal to 0. That is, RHS will be 0. Then it is called a homogeneous system. We see that if you put x equal to 0, then it will satisfy this equation because A into 0 will be 0 and RHS is already 0. So x equal to 0 is always a solution. It is always a solution for a homogeneous system. And this solution is called, x equal to 0 is called the trivial solution. This is called the trivial solution. So, for a homogeneous system, that is a system of the form Ax equal to 0, x equal to 0 is always a solution and that is called the trivial solution. Now, we will once again see the statement of the theorem. A homogeneous system of n linear equations in n variables Ax equal to 0 has only the trivial solution if and only if A is non-singular. So it says that it already has the trivial solution. Now it has only the trivial solution if A is non-singular. So we will prove the sufficient part here. Okay. So suppose A is non-singular. So A is non-singular means determinant of A is not equal to 0 and A inverse exists. So in this case, we should have only the trivial solution. Okay. So the system of equation is Ax equal to 0. So we can multiply both sides with A inverse because A inverse exists. So we will get A inverse Ax equal to A inverse 0. Now this implies that Ix equal to 0, which means x equal to 0. So x equal to 0 means it is the trivial solution. So if A is non-singular, that is if determinant of A is not equal to 0, which implies that A inverse exists, then for a homogeneous system, when you multiply by it with inverse, we see that x equal to 0 is the only solution. So it means that we have only the trivial solution. If determinant of A is not equal to 0, we have only the trivial solution. So to get a non-trivial solution, what we should have? So from this, it is evident that from this theorem itself, it is evident that to get a non-trivial solution, we must have determinant of A equal to 0. Okay, so here we see that if A is non-singular, we have, if A is non-singular, there exists only one trivial solution, no other solution. So it means that to get another non-trivial solution, we must have determinant of A equal to 0. Now this is explained by the next theorem, which says about existence of non-trivial solution. Okay. So it says that a homogeneous system of n linear equations in n variables Ax equal to 0 has a non-trivial solution if and only if A is singular. So to have a non-trivial solution, so to have a non-trivial solution, what we should have that we should have that A must be singular. Singular means determinant of A should be equal to 0. So now we will see what we studied in this class. That is, in this section, we studied how to solve system of equation using inverse of the matrix. So we studied that if A is non-singular, and we have the system of equation written in the matrix form as Ax equal to B, then its solution is of the form x equal to A inverse of B. So this is the first thing that we studied. Then we studied about homogeneous systems, that is homogeneous system. They are system of equation with RHS as 0. They are of the form Ax equal to 0. So here the first point we note that x equal to 0 is always a solution. X equal to 0 is always a solution. Second thing we note that this system Ax equal to 0 will have only trivial solution. It will have only trivial solution if determinant of A is not equal to 0, which means that is A is non-singular. So if A is non-singular, it will have only trivial solution. First we note that Ax equal to 0 always has a solution. So this is a homogeneous system, always has a solution. Whatever be the value of A and X, it will always have a solution. And that solution is called the trivial solution. It is always there. And the system will have only the trivial solution. That is, no other non-trivial solution exists if A is non-singular. That is, if the determinant of A is not equal to 0. Now, what about to get non-trivial solution? To have non-trivial solution means solution other than x equal to 0. So to get a non-trivial solution, we must have that the non-trivial solution will be attained if determinant of A is equal to 0. That is, A is singular. It is equivalent to saying that the matrix A is singular. So if the matrix A is singular, there will exist a non-trivial solution. That is the solution other than 0. So we will stop here. Thank you.